So hello everyone, welcome back to the another lecture. So my name is Ashish and today we will see the second part of extended phase shift modulation in the DAP converter. So in the last class we have talked about the what is extended phase shift modulation, why there is a need of extended phase shift modulation, right? So we have seen that there is a problem in the single phase shift modulation. What is that problem? The back power flow problem, right? So how back power flow will cause a very significant amount of loss in the system, right? That we can't say loss, but basically the power what is coming from the input we are not fully utilized for the output purpose, right? So that is another kind of the problem. So because of this my system may get hit up and losses will be increased, right? So this is the basic thing which is happening in the single phase shift modulation. That is why researchers have come up with the extended phase shift modulation. What they have done, they have tried to adjust the phase shift between basically this S1 and S4. Initially in the single phase shift modulation, S1 and S4 are turned on at the same time, and basically Q1 and Q4 are turned on at the same time. But in single phase shift modulation this is the case. But when they go for the extended phase shift modulation, they have introduced this one phase shift, that is in between the S1 and S4, and we have seen that S4 is turned on first and then after some delay S1 is turned on. Then S1 and S3 are complementary to each other, and basically S1 and S2 are complementary to each other. But basically Q1 and Q4 are turned on at the same time and Q2 and Q3 are turned on at the same time. So this is what they have done and what they have observed with this. So when we operate our system and give the gate pulses in this manner, what is happening, that back power flow is reducing. Okay, so this is what we have seen. So back power flow is basically very minimum that we have observed in the waveform. Okay, then the question is what where we left last time is that the phase shift between the first bridge and second bridge is D2 we marked, and phase shift between the this S1 and S4 we marked as a D1. Now we understood that okay, by providing the D1 and D2 phase shift we can basically achieve the extended phase shift modulation, right? But what is that particular duration of D1 and D2? How much phase shift I can give so that I can achieve the desired power? Okay, so that is the thing we are going to learn in this particular video. Okay, so what is the overall theme of this video is, we will started with some key waveform of the extended phase shift modulation, the same waveform which we have seen in the last class. Then some important expression in the extended phase shift modulation, like what is the maximum power flow expression, what is the current expression. We are not going to go in detail to how to derive those things, okay, but I will just quickly show you what are those expressions. Okay, and then we will see the SPS versus EPS. So what are the formulas in the single phase shift modulation, what are the formulas in the extended phase shift modulation, whether there is a very huge difference between the formulas in those two or all, that part we are going to cover. And next, most important thing, how to compute the D1 and D2, that part we are going to see. Okay, because if we know what is the D1 and D2, then only we can proceed for the MATLAB simulation. Okay, so here we are going to do the open loop MATLAB simulation in the next class. I have ready MATLAB simulation, just the time is the constraint, I need to record it properly. Okay, and sometimes the space situation nearby me, so that is also the factor which are important. Okay, otherwise how I can record the videos, right? So how to compute the D1 and D2, that is the another thing we are going to learn. Okay, so one reference I am going to use throughout this extended phase shift modulation discussion, and if you want you can go to that reference as well. Okay, just after the start of the video I am going to tell you that particular reference and what exactly the things are written down in that reference. We are going to go one by one. Okay, and we have, after end of this video, we have overall idea. Okay, this is how we will compute the D1, this is how we will compute the D2. Now I can do the open loop MATLAB simulation. So this is the word from your side. Okay, so let's get started with this video. So here we are in another window. Now we are going to start one by one. Okay, so this is the reference which I am using, okay, for overall discussion. So you can refer this paper. This is really good paper, and I am trying to explain this paper only. Okay, and we will try to implement whatever concept explained in this paper, those things also we are going to discuss. This paper is the extended phase shift control in isolated bidirectional DC to DC converter for power distribution in microgrid. So this is, I guess, first paper on the extended phase shift modulation which I have found. There are many paper on the extended phase shift modulation, but this is the first and basic paper, okay, from where how they originate the idea of the extended phase shift modulation and all. Okay, now we will start one by one. So in the last class we have seen that, okay, this is the my DAP converter and these are the some nomenclature we have. Then we discuss that, okay, this is how S1 and S4 are, basically S4 we will turn on first, and then after D1 THS time period we will turn on the second pulse, okay, that is the S1. And when S1 and S4 are turned on, that time only my power is going to be flow, and all these things we have seen. Similarly, there is a phase shift between the S2 and S4 as well, okay. Then Q1 Q4 are operated at the same time, Q2 Q3 are operated at the same time. So this we have seen. Then if we apply the KVL, we can give the VH1. So this is the VH1 and this is the VH2, okay, and subtraction of both these we are going to get the VL waveform, okay. VH1 minus VH2 will give us the overall waveform of the VL. So that part we have already seen, okay. What is my turns ratio? N/1. Then based on the waveform of the VL, I can compute the waveform of the IL, and this you know how exactly we are going to get. And what we have seen that basically back power flow is here near B equals to 0 when we operate it in the single extended phase shift modulation. How exactly this is coming and all these things we have covered in the previous lecture, okay. So that is not the part I am going to repeat in this lecture, but I just I have to complete the story. That's why I am just showing you, okay, these are the things which we have seen, and if you wanted to recall this thing, you just watch the previous video, okay, so that you can link the overall discussion, okay. Now basically in the single phase shift modulation we have derived the expression of the current IL, okay. What is the current IL expression, what is the power expression, okay, and what is the maximum power expression, all these things we have derived in the single phase shift modulation. So if you wanted to do the derivation how we can derive for the extended phase shift modulation, you can watch that video and then you can apply those concept on these waveforms, okay. If you apply the concept on these waveforms, you can easily do the things, okay, you can easily derive the things. But my motto here is not to derive the thing, I wanted to just show you few important things, okay. So when my DAP converter is operating the basically extended phase shift modulation, the expression for the current IL at T0, okay, the expression of the current is basically this particular formula. So what are the different terms involved here? D1, D2, okay. So D1 is there, D2 is there. Where D2 is what? My D2 is a basically phase shift between the this primary bridge and secondary bridge. What is D1? D1 is the phase shift between this S1 and S4, okay. Just keep this nomenclature in your mind, okay, don't get confused. We will build if you are getting confusion, don't worry, just watch this video completely. At the end of this lecture you will have a clear cut story in your mind, okay. So we have this expression of the IL. Now here most important thing is you just understand Fs. What is Fs? Is my switching frequency, but this Fs is equal to 1 upon 2 Th. What is THS? So THS is nothing but the TS by 2. So very important thing here is that when we go for calculation of D1 and D2, it is its total time period should be equal to TS by 2, okay, or it should be less than TS by 2. That is the first constraint you should understand, because D1 and D2 are my delays, right. These are the delays. You can see that basically S1 and S4 there is some delay, so this is some time. Then basically S1 and Q1 there is a some delay, so that is another time. So this time is not equal to D1 plus D2 time is not equal to overall TS, that is my switching time, okay. It is always equal to TS by 2. That is the first thing you should understand, okay. So I have mentioned here that Vs Fs is equal to 1 upon 2 THS is a switching frequency, and here K is my voltage conversion ratio. So what is the value of the K? K is a V1 divided by N into the V2, okay. So this is factor is again important, because this factor is we are going to have in our expressions, okay. So what we have learned so far, so now basically we have started this video, we have understood some background, okay. Now we have come up with one expression, okay, which is well known expression. We can derive this expression as well, that is not a big issue, okay. And only thing, one more important thing, last time when we are doing, we are multiplying some constant multiplied by the TS, right. So total time period. But now here this time period is not the TS, it is TS by 2. That part you need to understand, okay, which we called here it as a THS, okay, and which is equal to TS by 2. Okay, I hope so. So far so now the discussion is clear. Now we will move forward. So from the current expression, you know how to go for the power expression. Okay, so the power expression is again 1 upon THS integration 0 to THS VH1 IL of T into the dt. Okay, and if you do the integration and all, you are going to get one expression of the power, and this is the expression. So we are not interested here to deriving the thing, we just wanted to have some important expressions. Okay, so we have the important expression of the current with us, and now we have the expression of the power which is marked as a p dash. So what is the expression? So this is some sort of expression is there which involve the my k coefficient. I feel no, there is no k coefficient. D1 is there, D2 is there. Okay, so this is the overall expression. Now what we wanted to understand, what is the maximum power? Basically this can be flow from in the extended phase shift modulation, whether it is the same of the single phase shift modulation or this expression is going to be different. Okay, so recall the expressions of the single phase shift modulation. What is the power flow in the single phase modulation? What is the maximum power flow in the single phase shift modulation? Those things you should keep in your mind. Okay, so because those things we have already learned. So this is the somewhat expression we have. Okay, now we wanted to understand what is the maximum power can be happen in the extended phase shift modulation. So what we are going to do, what is the general procedure? Find a stationary point of D1, optimize the inner phase shift part of fixed D2. So let us say we have the fixed D2 and we are optimizing the D1. So what we are going to do, treat D2 as a fix, differentiate P dash with respect to the D1. So why I am basically fixing the D2? Because we know that when we go for the single phase shift modulation, this D2 is the phase shift between my primary side bridge and secondary side bridge. So here what we are assuming that my phase shift between the primary side bridge and secondary side bridge is fixed, just like the single phase shift modulation. Now I wanted to find out what is the maximum basically D1 between the S1 and S4 I can provide, so that I can get the maximum power. Okay, so this is the fundamental thing, and we know that what is the value of the D2 for maximum power in the single phase shift, it is a 0.5. Okay, so same we are going to use. So I am differentiating it, okay, and I am getting some particular thing. Now basically we know that set 0 for the stationary point. So I am finding out the stationary point. So this is the one of the condition we are getting. So D1 is equal to 1 minus 2 D2 divided by 2. So what usually people do, people will do the things and stuff from here only. How they approach? So they calculate the basically outer phase shift, like the D2 they calculate initially in MATLAB, and they will just keep the values here and find out the D1 and try to run the simulation. Okay, but that is not the general, that is not the correct way. We can go with this, not for that is for sure, but these are the some stationary point. We cannot say that at this particular D2 whatever we have got in the single phase shift, just putting in this formula and calculating the D1 and using those terms in this MATLAB will give us the answer. Okay, will give us the proper power transfer. So that is not the case. Okay, so there are some other expression which we need to see, those expression we are basically targeting. Okay, so this is the stationary point condition. So what is the important thing here is that this particular one condition, and another is this D1 plus D2 star should be less than or equal to 1, and this 1 corresponding to the TS by 2. Again and again I am telling, okay, this is corresponding to the TS by 2. It is not the TS. Okay, it is a THS. THS is nothing but the TS by 2. Okay, so half of the time period. So constraint on this is this value should not be greater than TS by 2, and this is equals to 1. Okay, so that is the for sure. Now basically what we are going to do, substituting this value of the D1 star in P dash, and we will try to solve this. So this is just pure maths I am solving here. So I am not just, you can observe the things. So I am just putting basically I have my this expression of the P dash. So instead of the D1 I am keeping this particular expression and just trying to solve it. Okay, and once I am solving it, what at the end of the this particular solution what I am going to get. So you can just observe what is written down here. If you have any query, you can ask me in the comment. I will try to explain the things. Okay, because this is pure maths. We are all engineer, we are all researchers, so we know how to do the maths. Okay, so we are here to learn the concepts. So now after solving this maths, so what I am getting is that this is somewhat expression I am getting. Okay, so this is the basically somewhat expression I am getting. Okay, now maximize over d2 and find the global maxima. So to find the global maxima, we know that what is the value of the d2. D2 is 0.5. Okay, in single phase shift modulation, maximum power we are going to get at d equal to 0.5. Okay, so now here my d is nothing but the d2, so I will just going to put the d2 equal to 1 by 2, that is 0.5, and I am simplifying it. So what I am going to get the expression is that my maximum power is nothing but the n v1 v2 divided by 8 fsl. This is the same as the single phase shift modulation. So you can observe that maximum power transfer in the single phase shift modulation is equals to maximum power transfer in the extended phase shift modulation. So both are coming to be same. Okay, so this is what I have written down here. That exactly matches with the traditional phase shift or single phase shift maximum power expression. EPS does not increase the theoretically absolute maximum power, instead enlarging the set of d1 d2 that can realize the given power and yet reduce the back power flow. Okay, so this approach is not to improve your or increase the maximum power. The most important part of this is to basically reduce the back power flow. Okay, back flow power or current stresses. Okay, so how the current stresses are related, that we will come. Okay, but mostly what is important thing in your mind is that we need to reduce the back power flow in the using the extended phase shift modulation. Okay, so this is the constraint we have, and this is how we will work. Okay, so if we put the d1 equal to 0 and d2 equal to 1 by 2, that is exactly the traditional phase shift modulation we have. Okay, so this is how we reached up to the basically maximum power transfer expression in the extended phase shift modulation, and this is same as the single phase shift modulation. Okay, now how exactly this is related to the basically single phase shift? So you know that basically in single phase shift modulation, this is the my expression of the power flow. Okay, so maybe there we have used del or d, I am not under, I don't remember, but just relate. If you have noted down the things, that will be pretty much clear. Okay, because you should have the side by side comparison. So for traditional single phase shift modulation, this is the expression, and what is the maximum power flow there, this is the maximum power flow, and if I will do the p SPS divided by the p max, this is the term I am going to get. Okay, and using the this term only, we can calculate what is the value of the d2 we can have. Okay, so this is the overall story. Similarly, for extended phase shift modulation, we calculate the value of the P dash and we calculate the value of the P max, and if we divide both of them, this is the overall formula I am going to get. Okay, so these two expressions are also very important. So you can have just side by side comparison of the SPS and EPS. Okay, what is the maximum power flow and what is the basically overall power expression for the basically single phase shift modulation as well as the extended phase shift modulation. So far so now what we have seen, we have learned about the extended phase shift modulation, why this extended phase shift modulation is important, and how basically it will reduce the back power flow through its operational waveforms. Okay, so that part you have clear. Second thing we have learned is basically what are the important expressions we need to keep in our mind when we go for the extended phase shift modulation. Okay, so these are the few expressions which we have understood. Now we will learn the third part, how to compute the d1 and d2. Okay, so there is a standard procedure to go for. Okay, where the closed looping is needed and where the open loop we can do, that all part we are going to discuss. But in this playlist we mostly cover this video, and after that basically open loop simulation, where I will just demonstrate each and everything. Then maybe in future we will start with the closed loop simulation, but I wanted to complete the next dual phase shift modulation strategy. Okay, so after this video we will just do the open loop simulation. Okay, and then we will go for the double phase shift, and how to implement this extended phase shift in the closed loop form, that we will see. I will just give you the approach how you can do, but I will not say I'm going to make a video right now. We will make a video for sure. If you come after 6 months on this channel, you will definitely find the video of the extended phase shift modulation and in closed loop as well. But as the time is the constraint, and I wanted to make this playlist basically as comprehensive as possible, so whatever things I have planned initially to deliver, that thing we will going to cover first. Okay, so let's get started with this, how to compute the d1 and d2. Okay, so here we are. now very important thing, okay, you just note it down step by step, okay, because I am going to discuss in detail how I am going to compute the d1 and d2, and based on that I have prepared one script for me, okay, and I'm expecting that you people are also going to prepare the script for yourself, okay, because every time a parameter we are going to change, I'm not going to calculate the things d1 and d2 manually. You need to prepare a robust script, okay. Take your time, try to learn how to make a script effective, okay, because once that is done, that is for you, okay, you can use it as many time as possible, okay, and it is somewhat basically very important to have your script, okay. I will basically, I am okay to share the script, but I want you people to write down by your own, okay. Otherwise it is very easy for me just to basically copy somewhere and paste it and give you as a link of the overall script file, and then you can basically just run the simulation, but that is not the ultimate motto of this channel. I want you to learn the things, okay, so that is the thing I want from you, okay, because you are learning sincerely, passionately, and that's why I think you can do, and you can create your own script, okay. So my task is to make your life easy just by explaining and putting the things in a very good manner, okay. So let's get started with this. Apart from all these things, so how to compute the d1 and d2. So what is the step one? Define the system requirement, okay. So you have your system, so you will just define your system requirement, like what is the v1 voltage, what is your v2 voltage, what is my required power, what is my turns ratio, and what is my switching frequency. Another important parameter is what is my L leakage, okay. So what is my L leakage, okay. So I already told you that, okay, so here it is mentioned, or in a script also I'm going to write it down, like n is equal to basically n primary is to n secondary, which is nothing but the v1 is to v2. But when we go for hardware designing, the parameter is fixed, okay. So you have to choose your turns ratio is very carefully. If you are choosing 1 is to 1, then irrespective of v1 and v2, whether your v1 and v2 are changing or not, my performance of the system should not degrade, okay. So that thing we need to keep in your mind. So every time basically I can basically keep v1 by v2, so that's fine, but in hardware that is not going to happen. Similarly, leakage value, L leakage. So L leakage also, once you are going to design, so transformer design for the DAB is also really interesting. So at the end of this basically playlist, I'm going to make a video on how to design the transformer for the DAB converter, because we are not going to buy the transformer, so we are going to make by your own, and that is the thing we usually do, okay. So inductor design, transformer design, these are the things which we should actually learn and basically make. So these parameters are not going to the change. What I wanted to say, that once you design the hardware, these parameters are not going to be changed, okay. In simulation, okay, you can change based on the values of v1 v2, you can change the value of the leakage inductance, you can change the value of the turns ratio, that's perfectly fine. But when you go for the hardware design, these parameters are fixed. Now your v1 and v2 is going to be changed with respect to what you want, okay. So that thing we have to keep in your mind. So while doing the simulation, we will make sure that we will basically initially, okay, we will change the n as well, we change the leakage as well, and then after 2-3 simulation result I show you with how exactly the things are happening, then we will basically keep n value as fixed, and then we will run the simulations, okay. So first step, you are pretty much clear that, okay, whatever the system requirement you have, that you have put, okay. Now this is all based on the whatever mentioned in the paper, okay. So I have told you the reference initially, so that same reference we are using as well, okay. Now step number 2, compute or choose the leakage inductance value, okay. So this leakage inductance value, you know that. So how we are going to calculate the leakage inductance in the single phase shift modulation, the same procedure I am going to use here, okay. So you know that we usually do the P maximum power, we assume something, okay, then we calculate the L for that particular maximum power, okay, and then what is my L required. So this is based on this particular formula, this is the same formula, okay, for single phase shift or for extended phase shift, maximum power formula is same, okay. And then we will use some basically alpha factor, okay, and this factor last time we have used 0.8, so 0.7 to 0.9 we can have this factor. And so what exactly the meaning of this factor? So at this particular L require, if I am achieving the 30 let us say my power requirement is suppose 30 kilowatt, so with this L value, if I am achieving the 30 kilowatt, So with the lower value than this, so if I will multiply it with the 0.8, with the lower value of this I can achieve some higher. So basically with this factor maybe I can achieve 35 kilowatt, 40 kilowatt. So this is what, because I don't want it to operate my system at the basically peak power. Okay, I always try to operate my system at some lower power. Let us say my maximum power transfer capability of the circuit or my DAP converter is 40 kilowatt. So based on that I will choose the value of the L lower value, so that I can easily, if its power maximum power at that particular L is 40 kilowatt, I can easily operate my DAP converter at 30 kilowatt. Okay, so that which is my required power output. Okay, so that's why this factor L is there, and this we have discussed in the single phase shift modulation as well. Okay, so once we have come up with the value of the L, we are fine. Okay, that's it. And then we are not going to change the value of the L, because in hardware we are not actually have the provision to change the value. So why should we change? Okay, right. So this thing is also there, so we are not going to change the value. Okay, once we compute this. Now second thing, compute the derived ratio and normalization. So what this paper have done is that the overall calculation how the d1 and d2 is computed, that is completely based on normalized power. Okay, so he is not look for v1 v2, what is my normalized power. Based on that normalized power only other calculations are calculated. So we already talked about, so these all things you need to write it down in the script file. Okay, so try to make your own script file as already I told you, and try to keep this thing in a series, step 1, step 2, step 3, and gradually you will come up with that. Okay, my entire script is ready for basically MATLAB simulation. So voltage conversion ratio K, which is again important for us, so which is V1 divided by N into the V2, you compute. Then normalize constant, so this is from the paper, so Pn is equal to, this is the maximum power which can be possible. Okay, and at what L we are going to choose, maybe my required power is a 30 kilowatt, so based on the L which I am going to choose, which is basically 0.8 multiplied, so it is always higher value. So this normalized power is always going to be greater than. Okay, so it is maybe 35 38 kilowatt, some sort of. Then normalized required power is basically P required, it is just sort of the per unit system I am going to convert. Okay, the P required divided by the P normalized. So let us say my required power is 30 kilowatt and my normalized power is 40 kilowatt, so 3 by 4, so 0.75 is my required power. And the overall procedure, overall derivation is there in such a way that basically it will use this P required value only. Okay, this 0.7 0.8 whatever number come, that is the thing which we are going to use for the further things. Okay, now next thing is generate an initial guesses for d1 and d2. So how the algorithm is given for the extended phase shift modulation, I'm thinking that okay, this video is basically bit of basically it should not go about your head. Okay, because this is somewhat difficult to understand. You watch once twice this video, you will understand everything. Okay, I have tried to put everything in one video. I hope so. This video is almost 30 minutes, maybe we needed another 10 minutes to finish the video, but you should try to concentrate and try to understand. Okay, once you understand, those who wanted to go for the extended phase shift, they will understand everything. Okay, so far so now we understood what we have done. Now what we need to start with. Okay, so this is somewhat we are going for the closed loop implementation. Okay, but we are not going to do the closed loop, but how the process is we need to understand. Okay, so generate an initial guess for d1 and d2. Now how to generate the initial guesses for d1 and d2? So for the d2 we already know how we have calculated for the single phase shift modulation, you understood. So the same d2 value I am going to assign. Whatever we have done for the single phase shift modulation, the same value of the d2 I am going to assign. Now I want the value of the d1. So from where I should get the value of the d1? So this is the same formula we have seen, right? You understood the same thing we can calculate here as the d2, or you can use this particular formula to find out the value of the d2. Okay, so this is the initial guess of the d2. Okay, I hope so you understood so far so now. So either you start with the single phase shift modulation d2, or use this basic procedure which will ultimately give you the same value of the d2. Okay, so these are the initial guess. I am not saying this is the exact value which we are going to use, but these are the initial guess we need to give to our system. Okay, so d2 we have calculated, and this should be less than 0.5. Okay, because overall we need to have the addition of the d2 plus d1 is equal to 1, which is less than equals to 1, and which is equal to ds by 2, right? Then second, you can start with the inner basically phase shift as 0, or you can compute with the help of this particular formula for zero backflow condition. So this is the condition for zero backward power flow. Okay, so this is mentioned in the paper, so you can use this condition. Okay, so we have calculated the value of the d2. Now start with the analytical zero back power flow choice. Okay, so this is the formula which is mentioned in the paper. You can use this. Okay, this is well known derived formula for the extended phase shift modulation. So from that you can get this particular expression of the d1. So d1 is equal to 1 minus in bracket 1 minus 2 d2 divided by the k, and what is k and what is d2 you already know. So from there you can have the basically value of the d1 as well. So you have two initial cases. Okay, so one is a d2 initial case and another is the d1 initial case. Okay, so if you use this value to run your simulation, might be you are going to get the desired power, desired output, but what will be the happen, your zero back power flow may not be equals to zero. Why? Because we have not optimized it. Okay, we might get some values but we have not optimized it. So d1 d2 we calculate, we can use those value directly in our system, but those are not optimized values. Now how to optimize this? Now let us go for our understanding the EPS power flow equation. So step number 5. So step number 5 is understanding the EPS power flow equation. So we have this particular power, normalized power, okay, P dash, which is basically P actual divided by the maximum power. So this number is always less than equals to 1. Okay, and this is the thing which we have already derived as well. Now what we are going to do, basically this is the constraint we have. Okay, so how we are going to proceed further? So once we have initial case of d1 and d2, we are going to put those value here and we will try to find out what is the value of the p. Okay, and we will try to check this constraint, so whether this is lies between this particular thing or not. This thing I have already discussed with you. Okay, that d equal to 1 corresponding to the ts by 2. Okay, that we have already seen. Now most important thing come, like we need to optimize the things. What is the meaning of optimization? We need to choose the value of the d1 and d2 in such a way that basically it will basically check all these three conditions. What are these three conditions? I will come. So we need to perform the grid search. Okay, so there in MATLAB there is option of the grid search. You can just basically chat GPT or Google it, basically how to write the code for the grid searching. Okay, once we have the some initial case of d1 and d2, how we can go for the grid searching operation. Okay, and using the grid search, what we going to get some optimum points of the d1 and d2, we can find it out. So these thing we need to implement in the closed loop, like the lookup table. So if we have the multiple data point, we can just plot them, and basically based on whatever the parameter output of the controller we are going to get, based on that we will grid search in the lookup table, and then it will generate the two d1 and d2 value for us when we go for the closed looping. Okay, but right now we are doing it in MATLAB code. Okay, how to get the value of the d1 and d2. So we construct, basically this is our condition we already know, and d1 plus d2 less than or equal to 1. This is the another point. Then we compute the d1 and d2, and we will try to normalize power P dash, normalize back power flow, and normalize current state. So these are the three conditions. What are the expression for these three conditions? I will just show you, and we will check that whether my P dash minus P require is less than or equal to some tolerance level we have or not. Okay, so that thing we need to understand. What is exactly this? I will just show you. So these are the two a constraint we have, and we need to basically compute the value of the d1 and d2 and try to keep those value here and see whether it is in the permissible tolerance range or not. If not, then I need to change the value of the d1 and d2, and I have to find out the best suitable match. And this is the error and trial method, but we don't have to do this. We can do it with the help of the code. Okay, if we have the controller, then that controller automatically do all these stuffs. Okay, but now we are going to implement the open loop simulation of this. We need to write some MATLAB code which will give a optimum value of the d1 and d2. So for each pair of d1 and d2, I am going to compute this my back power flow and current stress normalization. Okay, and for back power flow I am going to get some solution of the d1 and d2. For this I am going to get some solution of the d1 and d2, and this is how the process will continue. And then based on this we will at the end our script file will going to give if you have the controller, that controller automatically will find out the best suitable candidate of d1 and d2, so that I can achieve my maximum so that I can achieve my desired output power. Okay, but here basically our script file we are going to get, and which will give you the value of the D1 and D2, which will have minimum back power flow, and another value of the D1 and D2 which will have the minimum current stresses as well. Okay, and this is how it will continue, and then we need to choose the value of the D1 and D2, and this is the basically what I would say, this is somewhat approximate. So we need to basically try to choose here and there value of the D1 and D2, so that we can reach to our basically actual power, because this script is there but it will choose some random values, right? Because this is the grid searching, whatever base combination it has, and if it is satisfies the condition, it will collect those points, right? So, and it will try to use those points, but those are not actual point. We need to just basically multiply it with the 0.9 or 0.8, so just some sort of small multiplication we needed to get the actual power. Okay, how to implement in the MATLAB, that we were going to see, and then we can generate the gate pulses, just D1 multiplied by TS by 2 and D2 multiplied by TS by 2, and then we are going to give to our bridges, and our simulation will work. Okay, so these are the 9 steps which you need to basically write it down in a really good way in a MATLAB script. I know this is somewhat difficult. If I feel then I will give my entire script to you as well. Okay, how we are going to, but I want you to write first and just comment it out, sir, I have written down something, I am facing the problem here, so I can actually know that okay, at what part you are going to face the problem. Okay, and then I'm ready to give the entire script, because I know the writing the script is tough task, and it will take time as well. Okay, so you have 1 or 2 days of time. After 2 days I will upload the another video. Okay, but I want you to write it down in a comment that okay sir, we have tried, and whether you have written down or not, that's perfectly fine, but at least you should try. Okay, because if you are not trying right now, and if you are not learning right now, then when you will going to learn? Okay, because these are very basic simple projects, right? When you go for actual tough tasks, then how you are going to do? Okay, so mostly I think you can do this few steps, like the generation of the initial gas up to the step number 4 you can easily do. For step number 5 also you can easily do. From step number 6 you need to have some more knowledge about how to write down the code. Okay, so how to form the grid, then how to collect and how to compute with this particular thing, and how to choose the best optimum solution. So those things maybe I can help you to write it down the script, but apart from this I'm pretty much sure that you can write it down the things. Okay, and rest of the things are very easy for you. So this is the one of the result of the MATLAB which I got, and I have tried to see this in the LT Plex as well, and there I have seen that back power flow is almost equals to 0, and this is the somewhat expected waveform we should have in the next class. Okay, so in the next lecture we are going to see all these things. So with this I will conclude this lecture, and see you in the next class. One more thing I wanted to just share you, that basically I have seen that so many people talk in the chat, which is really good thing, because somebody sometime it is not possible for me to reply in the basically comment, because I'm a bit of busy in some other stuff. So I have seen that few people are helping other, which is really good thing, and I'm encouraging this, that if somebody asks some doubt and if you know about that concept, you can reply to them. Okay, that will be better, because at the end of the day we have to help each other, then only we can grow as a power electronics community. Okay, so that is only the wish I have, and you can connect with me on LinkedIn. So many people connected, thanks to all of you, and you ask me really nice questions, and which motivates me to make another videos, right? Because when question come to me, it is like, okay, how I can answer this. So that is the first thought I came in my mind. So, and this will motivate me to okay, to brainstorm myself, and look into the different things, and then come up with something new. Okay, so with this I will conclude this lecture. Thanks for watching this video. Share with your friends, those who are watching and those wanted to learn the DAP converter from very basics, and take care, and thanks for watching.